All right. Good morning, everybody. Happy Krishnastami. So let's get started with the DLCO Unit 1. All right. Just going to post this in the WhatsApp group. After that, we'll get started. All right. And now let me pop out this chart. All right. And now let me pop out this chart. Yep. Right. Um, I'll do it the usual way. Yeah, in the previous class, we had done Java. If you didn't see that, just have a look at that. So, net one, this works. And I am thinking of making the live in entirely English for a week. I just need to compare the reach of when I'm doing it in entirely English and when I'm mixing both Telugu and English, so that we will do what is the best, right? Because I need this to get to as many audience as possible, right? And, yeah, we will do what is best for our channel then. Yeah, this thing is useless. All right, got this. So at our presentation, so it is basically how you represent data, and binary numbers, fixed point representation, floating point representation, number based conversions, okay, sure. Yeah. So yeah, binary bits. It is the way of representing using binary bits. I think we have the DLCO nodes here. I think we already know this thing before, but I'm just writing here. Binary base to 0 or 1. Each digit is called a bit. The position of each bit represents a power of 2. Starting from, yeah, let's look at an example 1000101. That is 1 into 2 power 0 plus 2 power 1, 2 power 2. 1 into 2 power 2 plus, right, 0, 1, 2, 3, 4, 5. 1 into 2 power 5, right? It is 1 plus 4 plus, and this is what? 2 cube is 8, 2 power 4 is 16, 2 power 5 is 32. So 37, right? This should be 37 according to binary. This one number 0, 1, 0, 1, and decimal. Oh, my bad. 37, sure. And what is fixed point representation? The method of encoding real numbers in computer system where the position of decimal is fixed, allowing for consistent representations. Okay. So fixed point representation is basically way of representing real numbers. The position of the decimal or the binary, the position of the decimal point is fixed. That's what it means, right? Yeah. Let's take an example. 26.5. How do you do this, right? We use the traditional way. I hope you have learned this in B.Triple. 13, 0, 2, 6 are 12, and that is 1, 2, 3 are 6, that is 0, 2, 1 are 2, and that is 1. 11010. Yeah, that's true. 11010 point, and this is 0.5 remaining. And for decimals, you do the multiplication 1.0, that is 1.1. That's it. Because you got the after decimal as 0, right? Yeah. And let us take one more example, 47.36. This will be more complicated, I think, but let's do it. 2. 23 is 46, and one remainder. 2, 11, 22, that's one remainder. And 2, 5 are 10, that's one remainder. 2, 2s are 4, that's one remainder. And 2, 1s are 2, that's 0 remainder. So that is 10, 4 ones. Is that it? Point. And I got to do the 0.36 times 2. That's what? 0.72. So you got the 0 here. And 0.72 times 2 is what? 1 point, 1 point, 1.44. That's it. I got a 1 then. 0.44 times 2 is 0.88. You got a 0. And 0.88 times 2 is 16. 1.76. Right. So 1. So you got 0, 1, 0, 1. Let's see 47.36 in decimal. What is the decimal? Sorry, I mean in binary. Yeah, 1041.0101. Sure, that's how this works. So that is basically the fixed point representation. Sorry, I'm having a little cold. And floating point representation. Computers handle real numbers with large values. Okay. Yeah, I think I have written something on this yesterday. I don't think we are actually going to look at how the floating point representation works. We'll just look at the formula and its significance and the IEEE 754, the standard Institute of Electrical and Electronics Engineering. They have devised a standard way of doing this. Right, helps computers handle real numbers with large range of values. Helps to denote either very large or very small values. The single precision format, I think we have studied this in C and Java as well. Single precision uses 32 bits or 4 bytes, and the double precision uses 64 bits or 8 bytes to represent the data. Larger range. Obviously, the double precision has larger range than the single precision. Scientific notation within a single bit. Sure, the representation is based on the scientific notation. Okay. And a finite number can also be represented by 4 integer components. Okay. So sign into significant. What is significant? I think I had another formula. Yeah, they called it mantissa, right? Yes, here the significant is also called as mantissa. So the formula is value is equals to sign. This is either positive or negative times significant or mantissa into base to the power of exponent. This is how we represent it. Right? Sign indicates whether positive or negative, and significant or mantissa represent the precision bits, obviously. That is a well prepared class. Base usually 2 for binary, and in case of decimal it will be 10 for decimal. Yeah, and exponent. Basically, this exponent determines the value. Yeah, determines the scale of number. So it says how big or how small the number is. That's it. And the IEEE 754 representation. So yeah, that if you use like more technical words, then the examiner is going to understand that you have understood the concept. So just yeah, writing this wouldn't hurt, right? So single precision order 32 bits, right? The base takes 2 bit. Sorry. Okay. 23 bits for what? For significant. And 8 bits for exponent. 1 bit for sign. This is how the single operation works, and the total is 32 bits. Sure. And is there, yeah, there is double precision as well. Okay. And how is here? The double precision, I think it will be just double 52 bits per significant. 11 bits for exponent and 1 bit for sign. Okay, we see. So did it make 64 bits? Yeah, 52, 63, 64 bits. Nice. Yeah, okay, I think this represents infinity. I think this is enough for the floating point representation. Number-based conversions. Number-based conversions. Okay, yeah, the classic thing. I think we have already studied all of this before, but let's do this once again. Number-based conversions. So decimal, it is base 10. Binary, it is base 2. Octal, it is base 8. Hexadecimal, this is base 16. Alright. And this is all theory. I think we can write this. Just let's look at the conversions actually. Decimal number system to binary number system. Let's say we got 16. How do you convert to binary? You just divide it with 2 repeatedly. 2 8s are 16. That gives a remainder of 0. 2 4s are 8. That gives a remainder of 0. And 2 2s are 4. That gives a remainder of 0. 2 1s are 2. That gives a remainder of 0. So 1 double 0 double 0. Right. That is the decimal point representation. You can expand it from binary to decimal as well. So take 1 double 0 double 0. So this is 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4. 1 into 2 power 4, that is 16. That's how you get it. Decimal to binary, binary to decimal is completed. And decimals to octal. Let's say we got 57. How do you convert it to octal? Divide it by 8. 8 6 are 48, 8 7s are 56, right? That gives a remainder of 1. So that is 71 in octal form. And convert octal to decimal now. So 71, right? 7 into 8 plus 1 into 1. And 56 plus 1, that's 57. That's it. And decimal to hexadecimal, how do you do it? Consider a big number, 279. Just divide it by 16. 16 ones are 16. This is 4 plus, oh my god, 4 plus 7, that is 11, 119. 16 4 is 64, 16 6 is 96, 16 7s are 112. All right, 112 and 7. And 16 ones are 16, and that gives 1. So this is 1, 1, 7 to the base of 16. And hexadecimal to decimal, let's do it. 117, that is 1 into 256 plus 1 into 16 plus 7. 256 plus 16 is what? 16 plus 7 is what? 23. 256 plus 23 is 9. 279. So this is how you convert decimal number system to any number system and any number system to decimal number system. And then we get the octal and hexadecimal interconversions. Right, consider 279. How do you convert it to binary? So just divide it to 3 bits, right? The 2 is 010. The 7 is 111. Okay, first of all, 279 is not possible in octal because the base of octal should be less than 8. The base of octal is 8, so every number should be less than 8. So this number is not possible. I'm sorry. Let's take another number like octal to binary. We got to do this, right? 165. Let's say this. 1 is 001. 6 is 4 and 2, right? 110. 5 is 101. And this is how you convert it to binary. 165 octal to binary. Let's say this. Okay, 1110101. Exactly. You can discard the zeros on the leftmost. That is not an issue. And if you gotta do octal to hexadecimal, you first do octal to binary, and then you can do binary to hexadecimal. Let's see how this works. Because binary is like a solid base. Let's convert this to hexadecimal, right? Divide it into 4 bits. This is 4 and this is 4. What is the value of this one? 4 and 1. This is 5 and this is what? This is 7. So 165 octal to hexadecimal is 75. Yeah, 75. That's it. That is how you convert octal to hexadecimal. And octal to decimal is over. Octal to binary is over. And now hexadecimal to binary. Consider 7f. Right? Just what is the thing for f? That is 11 and 11. It is 15, right? And 7 is 0 111. So this is the thing for binary. 7f. It's to decimal. No, that's not decimal. I need a binary. 0 11141s. Exactly. And how do you convert hexadecimal to octal? First you convert hexadecimal to binary, and then you convert binary to octal. So here, what will you do? You will just slice up 3 bits, 1, 2, and 3, and you will add a 0 here and 1, 2, and 3. So this is 7, this is 7, this is 1. So that is 177 in octal. Yeah, 177. Nice. And binary to decimal, I think. Did we do that? Yeah, we did that. Okay, binary to octal, there is an easy way. Just combine 3 bits and write the number. That's how you do it. Let's say 0, 1, 0, 1, 0, 1. Slice up 3 bits and again 3 bits. What is this? 4 plus 1, 5, and this is 4 plus 1, 5, and that is 1. 155 in octal. 0, 1, 1, 0, 1, 0, 1 in octal. Yeah, that is 155. Cool. And we got binary to hexadecimal. Just do the same thing. Let's say convert it to 4 bits, slice up the 4 bits. That's it. This is 0, so no need to worry about it. 8 plus 2, this is 10. That means it is A. And 8 plus 4, this is 12. 13. 13 means 10A, 11B, 12C, 13D. So this is DA. 0, 1, 0, 1, 0, 1, 0, 1, 1, 0, 1, 0 in hex. That should be DA. Yes, nice. So this is how basically the number conversions work. And we have covered all the number conversions. Octal and hexadecimal numbers also we have covered. What are the components in data representation? What are the components in data representation? Okay, I don't know what this is, but signed binary numbers. So we will see 1's complement and 2's complement here. Sign magnitude representation. 1's complement and 2's complement. Yeah, this is all we got to see. Sign binary number representation. And let's see this. So there are mainly 3 ways of representing it. That is sign magnitude form, and 1's complement form, or you can write it like 1's complement. This is how you write it actually. and 2's complement method. So these are the ways of representing it. So the sign magnitude is basically the MSB is 0. That means the number is positive. If MSB is 1, number is negative. Remaining bits determine the magnitude. Let's look at an example, right? Let's say you got a 0, 1, 0, 1. Okay. So leave this MSB. This MSB means it is positive, and look at the remaining magnitude. So this is 1, 2, 4. 4 plus 1, that is 5. And now let's say you got 1, 1, 0, 1. Leave this 1, this means it is negative, and again 1, 0, 1 means 5. So that is negative 5. That's it. So for example, let's say 11011. This is negative, and 1, 2, 4, 8. So 8, 2, 10, and 11. So this is representation of minus 11. That's how you do it. So this is, what are the limitations? I mean, why did we invent one's complement again? This is very convenient, right? But the problem is, to represent 0, you have 0, this one, this means plus 0, and this means minus 0. So that is not how 0 works, right? You need to have only single representation for 0, because 0 is neither positive nor negative. Right. Yeah. See? And arithmetic operations become difficult due to separate handling of MSB. So you need to separately handle the MSB again, which is complicated to do. So it is difficult to implement in computers. And now let's look at the one's complement method. Positive, same as normal. Negative, how do you do it? Flip all the bits. That's it. So for example, plus 5 is what? 1, 0, 1. Or 0, 1, 0, 1. Right? And minus 5 is just flip all the bits 1, 0, 1, 0. That is it. So let's say 1, 0, 1, 0, 1, 0. What is this number? 1, 2, 4, 8, 16, 32. So 32 plus 8, that's 40, 42. So minus 42 will be 0, 1, 0, 1, 0, 1. That is minus 42 according to one's complement form. And it still got its limitations. 0, it can be represented as 0000. And it can be, we can flip all the bits. Sorry. 1111, this represent positive 0 and this represent negative 0. That is not possible. That is not how the representation should be. And arithmetic operations are difficult. And this as well. And so now let's look at 2's complement form. This is most widely used one. Right. Positive, same. Negative, do the ones complement, right? That is flip all the bits and then add 1 to the result. So if you add 1, then there won't be two representations for 0. That is our main problem and that will be solved. Got it. And here to get 5 again, 0, 1, 0, 1 and minus 5 will be first you do 1, 0, 1, 0 and then you add 1, that is 1, 0, 1, 1 is a representation for 5. See? And 0, you have only this one. Um, you cannot do this, right? Let's do the 2's complement for this one. Double one, double one. And if you add 1, you cannot do that. Because you need to then need an extra bit to do that. Right? Then it will become 100 0 or something. Because this is 15. And if you do plus 1, it will become 16. So there is only one representation for 0. And simplifies arithmetic operations because they can be performed directly without any special handling the sign bit. So that is how you represent negative numbers. And we have done with that. And let's look at binary codes and let's wrap this session up. Here we go. BCD, XS3, gray. Weighted binary system. Oh, all right. Way of representing data in binary format. So we got weighted codes. Right. The common 84214 2421 code, 5211 code, and we got BCD code, binary coded decimal, and we got XS3 code, and then we got gray code, and also we got error detecting and error correcting codes. We will look at them later, but now let's look at this. All right, I think, yeah, let me just open to this one. I want to get the DLCO right here. And the normal representation as well. That is unweighted format. Let's explore each of these things. Did we get any live chat today? Think so. Sure bro. కేమేవి ఇప్పుడు కాదులే తర్వాత చెప్తా. So let's look at the 8421 code. By this code, every decimal number is assigned a binary number. Right. Every decimal number has a 4-bit binary ranging from 0000 to 0 and 1001 to 9. You can write this table, right? And 2421 code for 0, that is going to be zeros, and for 1 it is going to be 0001. For 2 it is going to be 0010, and for 3 0011, and 4 it will be 0100, and for 5 it will be what? 4 plus 1, right? 0101. Okay, or you can do 1011. You see, why? That's the purpose of doing this. Because 1 is 5, and 4 and 1 is 5. Let's clarify this doubt. Yeah, it's simple part. 2, 4, 2, and the presentation. 5, it is given as 1011. We can also do 0101, right? Why is it thinking longer? Let's see. Icon code. Self-complementing scheme. What is self-complementing? Okay. The 0 to 4 becomes bit quarters. Okay. This is a self-complementing code. Okay, I see. So that means 0 to 4 are complements for 9 to 5. That means 0 is complement of 9, 1 is complement of 8, 2 is complement of 7, 3 is complement of 6, and 4 is complement of 5. So these two should be complement. That means the inversion. 0, 1, 0, 1, 0, 1. So 6, it should be complement of 3. So that is 1, 1, 0, and 7, that is complement of 2, that is 1, 1, 0, 1. Right, working. And 8 should be complement of 1, that is 1, 1, 0, and 9 should be complement of 0, 4 ones. So it is a self-complementing code, I see. And 5211. Is this also a self-complementing code? Yes, it is. So 0000, and just write the complement here. 1111, 527, and 0001, and that is 1110. Okay, and for 2, uh, so you can write 0011. If you write this, then this should be 1100. Actually, for 2, you can write this also, right? 0100 technically, but the complement will become 1011, which is also correct. Which is also correct, right? Yeah. Wow. And for 3, 2 plus 1, right? 0, 1, 0, 1, let's say. And then the 1, 0, 1, 0, 5 plus 1, 6. Cool. And for 4, 0, 111, right? Because 2 plus 2. And for 5, it will be 1, 000. Complements. Oh, nice. 8421, 2421, 5211. These codes are nice. So self-complementing. I have heard this term before actually, but I didn't know what that means. But now I understood what it meant. Okay, I think I removed the chart. My bad. A reflective code, okay. He has already mentioned it over here. Or 8421 is not a self-complementing code, just note it down. Is not self-complementing or reflective. So we have completed the non-weighted codes. I mean weighted codes, right? The non-weighted codes are simple. Just if you have some number like this, you multiply it with the positional weights. 2 power 0, 1 into 2 power 0 plus, 0 into 2 power 0 plus 1 into 2 power 1 plus 1 into 2 power 2 plus 0 into 2 power 3 plus 1 into 2 power 4. It will be 1. 1 into 2 is 2 plus 4 plus 16, that is 22. Right, let's check it over here. 1, 2, 4, 8, 16. 16 plus 4, 20. 20 plus 2 is 22. Right, that is how non-weighted codes work. We have been dealing with this from the starting of this lecture itself. And XS3 code. Just add 3. That's it. Let's say we got decimal BCD access 3. Let's fill this table up. 0000. Okay. Just need to put 10 here. That is 0000 and 1 0 0 0 1 2 0 0 1 0 3 0 0 1 1 4 0 1 0 0 5 0 1 0 1 6 0 1 1 0 7 0 1 1 8 1 0 0 9 1 0 0 1. Access 3 will be 0 plus 3 is 3. Just write these things down here. 0 0 1 1 0 1 0 0 0 1 0 1 0 1 1 0 and 0 1 1 1 0 0 1 0 0 1 and then just add 1 1 0 1 0 and 1 0 1 1 and 1 1 0 0. 9 plus 3 is 12 and this is a code for 12. That is a code for 9 in access3 format. That's how you do it. And gray code, it is a where one bit will be deferred, where only one bit is deferred. Let's write the gray code also here, shall we? Actually, it is written until 4 bits. Let's do it until 4 bits. 10, 11, 12, 13, 14, 15. For 10, it will be 1 0 1 0 and 11 1 0 1 1 and 1 1 0 0 1 1 0 1 triple 1 0 3 4 ones. And just write these things down here. 1 1 0 1 triple 1 0 4 ones. Okay, and for access 3, you gotta go to 5 bit. Because you have reached the end here. Alright, this is perfect. So what do is, you just write gray code, take the first bit as it is from the left and add these 2 bits to get the next bit. 0 plus 0 is 0, so it will be all zeros. So for 1 you do the same, just write 0 and add the 2 bits to get that. If you look at here, you will understand the difference. 0 and 0 plus 0 will be next bit, that is 0, and 0 plus 1 will be next bit, that is 1, and 1 plus 0 is 1. So this is the gray code. And if you look at this, no 2 bits have difference more than 1. So triple 0 1 and here this bit changed. The remaining bits are the same. So if you look at 3, just write 0. 0 plus 0 is 0. And 0 plus 1 is 1 and 1 plus 1 is 0. See, and if you look at this 1 and 0 are only the different bits. And then 4, 0. 0 plus 1 is 1, 1 plus 0 is 1 and 0 plus 0 is 0. And see, these 2 bits are different. That's it. That's how you do it. And for 5, 0, 0 plus 1 is 1, 1 plus 0 is 1, and 0 plus 1 again is 1. Right? And for 6, it is 0, 0 plus 1 is 1, 1 plus 1 is 0, 1. 1 plus 1 is 0, and 1 plus 0 is 1. And 0, 0 plus 1 is 1, 1 plus 1 is 0, 1 plus 1 is 0. As simple as that. You write 1 and again 1 and 0 and 0. These two bits are different, that's it. And for 9, you write 1, 1 plus 0, 0, 0 plus 0. Sorry, 1 plus 0 is what? God. Yeah. And 10, 1, 1, 1, 1. Nice. 1 plus 0, 1, 0 plus 1 is 1, 1 plus 1 is 0. 1, 1 plus 1 is 0, 1 plus 0 is 1, 0. And for 13, 1, 1 plus 1 is 0, 1 plus 0 is 1, 0 plus 1 is 1. 14, 1 plus 1 is 0, 1 plus 1 is 0, 0 is 1. Oh my god. 1, 1 plus 1 is 0, 1 plus 1 is 0, 1 plus 1 is 0. So this is how you do the gray code. I think this should be it. We got error detecting and error correcting codes. We will do them as well. And we will wrap this thing up.
Also, you can download this practice sheet from the link in the description below. Now open your Excel sheet and let's get started. So here I have the sample data of ID, name, department, salary, joining. MRF Zapper C1. Now for motorcycles. C1 to believe it. Date and performance rating. Now let's say I want to retrieve the first three rows. So I only want a first three rows here. So to get those first three rows, we'll use the take function. So this is the basic and simple usage that we can start with the take function. So here I'm going to write the formula equals take parenthesis, and then it asks for the array. In this case, array is the data, so I'll select all of these cells, and then a comma, and then it asks for rows. So we want the first three rows, so I'll simply write MRF Zapper C1. Now for motorcycles. C1 to believe it. Take 3 and close the parentheses. Once I hit enter, as you can see, we have the first
Something and we got to understand what this is.
function. Now let's say instead of
These are codes that can tell you something went wrong during transmission, but not always where or what went wrong. Add one extra bit parity bit to make total number of ones even or odd. Even parity data has 3 ones, so if you add one, it will become, yeah. If you what? If you add one, it will become 1 0, right? Yeah. One zero one triple zero 10. Oh, I see. N numbers are like how many numbers are there? 10. Sorry, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4. Okay, I see. Yeah, we're right there, detecting and error correcting codes and let's get this thing over with. Parity bit. Add one extra bit to make the total number of ones. Parity. That's how it works. Right? Consider the data. 10100001. 3 ones. Even. Sorry, 3 ones is odd, right? My bad. So add 1. It becomes 10100011. Example 1. Example 2. 10100011. 4 ones. Even parity. Add 0. 10100011. If a single bit error occurs, Parity mismatches. Limitations. Can't locate the errors. Cannot detect multiple bit errors. Let's say this is the code and the error we received as 100 100. Now it's odd, even parity as well. So it cannot detect multi-bit errors. And we got Hamming code. Single bit error correction. Yeah. It should work, right? Adds redundant parity bits, alright. So it's very nice. So this is a 7-bit Hamming code. P1 parity 1 2 power 0. P2 parity 2, this is 2 power 1. And P3 parity 3 to square. And this is D1 data 1, D2 data 2, D3 data 3, D4 data 4. P1 parity 1, D1 data 1. So 4-bit data can be encoded in 7-bit Hamming code. A 4-bit data in a 7-bit Hamming code. Example, consider 1011. What is it? This is 4, 2. Okay, 8421, right? 8 to 11. Now D1 is equals to 1, D2 is equals to 0, D3 is equals to 1, D4 is equals to 1. Compute parity bits. How do you compute parity bits in Hamming code? Let's see that. Covers bits where position binary bits has eldest be 1. 1357. Okay. 2367. Okay. Okay. Yeah. Now I remember it. Actually, we were thought about this in first year. Uh, so we got number and we got data. BCD, let's say 0 zeros 1 0 0 1 2 0 0 1 0 3 4. Yes, we had this hour. So 1 2 3 4 5 6 7. This is a 7-bit Hamming code, and the data that was given to us is 1011, right? This is P1, this is P2, this is P3. And just put down the data 1011. And now let's compute P1. One in rightmost bit. That is for 1357. So the position of 1 is P1, and 3 is filled with 1, 5 is filled with 0, 7 is filled with 1. So to make it even parity, P1 is equals to 0. 1 in second rightmost. So you should have 1 here. You have 2, and you have 3, and you have 6 and 7. 2 is P2, and 3 is 1. 6 is 1, 7 is 1. P2 is equals to 1 for even parity. P3, 1 in third rightmost. You gotta have 1 in here. 4, 4, 5, 6, 7. So 4 is P3, 5, 6, 7 is 0, 1, 1. So P3 is equals to 0 for even. So in this way, we will compute the values of P1, P2, and P3. P1 is, wait. What the heck is happening? P1 is equals to 0, P2 is equals to 1, P3 is equals to 0. So the Hamming code is 0, 1, 1 0 0 1 1 for 11. This is how we get it. So this is parity 1, this is parity 2, and this is parity 3, and this is data. Zero double one double zero double one. 0 double 1 double 0 double 1. Sure. So this is how we do the Hamming code. And we have completed the first part of Unit 1 of DLCO data representation. And we got digital logic circuits. We will do this later, man. And thank you